Okay, so let's start the second talk of the session. So we have Tom Abel with us from Stanford. So he's going to talk about practical fast beyond 2-point statistics for large scale structure clustering.
All right, thanks so much. Also, thank you to everybody for amazing teamwork across here. So I want to tell you a little bit about some new statistics that Arka and I started thinking about a few years back. And they, so I want to give you a rough sense of all the things we've done to convince ourselves this is something useful. To me, that's always good advice. When I can, I want to be brilliant, but that doesn't always work every day. And then on those other days, at least I want to be useful. And that's, I think, the spirit of this work. And I hope to convince you that that's true. So there's a whole slew of people that we sort of drawn into this with our enthusiasm for this. I'll highlight some of their contribution as they go along. Oh, yeah, it works. Okay, but very simple. It's a very minimal setup that we want to think about today. We start out, we have a collection of points. And the points are really boring. They all have the same weight. Same thing, there's no units associated to it. All we have, they're distributed in space. Space can be 1, 2, 3, 5, whatever dimension you want. But there's nothing special about any one of them. And we just want to be able to talk about how do these points fill space. We want to describe the clustering in a useful way and in a way that is also, communicates something to us as human beings. Because obviously we already have all the numbers for computers, the computer's already done. For the computer, it knows where all the points are. But we want to be able to argue about this and sort of describe, if we had another realization, we wanted to compare two of them, we want to sort of argue about, okay, do they similarly cluster in space? Or are both of them just homogeneously distributed or not? And sort of ask questions like that. And then in cosmology, we often have sort of this underlying motivation that we believe that there might be a continuous field underlying this. And where we get the points from is just withdrawing from a continuous field. So it's just a sampling of this underlying mass field. And so if we also have this property, that would be nice. If we can connect back between a continuous idea about where the points come from and the points. And of course, you all know the context of this, of all the surveys we've heard about, and we're collecting just crazy amounts of data on galaxies, hundreds of millions very soon with spectroscopic redshifts and billions with photometric redshift in the next few years. All right, so now one of the key lessons, I took away from this over the years is that really everything's a statistic. And so anything you do with a lot of numbers, if you have a lot of numbers, you add them all together, take the average, the mean, it's a summary statistic. It tells you something about these points. Arguably not very much because you averaged everything together and now it's just, all you've got left is maybe 3 numbers, mean X, mean Y, mean Z position. But fine, it's a statistic. You could compare it with the median and you could perhaps already learn something about your distribution. But literally any operation you can think of doing on all your data together potentially could be a useful statistic. So of course, that's a crazy situation. You have infinitely many ways of what you could do to your data. Now you want to think more about, okay, what are my metrics? What are the things I want to get out of the statistics I'm going to invent? Because I have certain purpose in mind and only I know, what are the good properties I need to have to answer these questions. And so a few, I think, that are good to keep in mind are, we want it to be informative. It should really, say something about the data. It shouldn't really wash out everything. So like in our example of just taking the mean. So if we have a mean RA and mean DEC of a survey, that's not very useful information. Because if I would have looked over here, then I have a different mean, or if I cut out a different anyhow, that's not great. But okay, we want it to be interpretable, so it should sort of make sense in our minds of what we're getting, right? So if I throw down a sphere of size 10 megaparsec, and I know the probability of finding exactly 3 galaxies in that sphere, what fraction of the time will have exactly 3 galaxies in there, that I can imagine in my head. That's like, okay, if I have a convolutional neural network or graph neural network that encodes all of this, and it has 8,000 weights, that's not very helpful to me. I mean, it's a great network maybe, and it might be useful for something, but it's hard for me to interpret what that says about the data. And also, I don't know how I'm going to compare that with a slightly different neural network that has 2 more weights, perhaps. Okay, it should also be predictable. So ideally, like when I have some cosmology, in our case, right, we have all these ideas about how dark matter behaves, how it clumps, and how it moves. They should have, at least the possibility to have sort of a theoretical framework of how to make predictions about what comes out of my statistics. It should be robust. So if I take one galaxy out, it shouldn't change everything in my statistic, right? If I add 10 more, it also shouldn't change everything dramatically. That's what I mean by robust. So it shouldn't be finicky, if you want. It should be fast to compute because we love trees. And so we want to be green with all our endeavors. Now, and of course, if it takes long, I'm also not going to do all the checks that I should be doing, because I won't wait for the computer if it takes 4 months, and then I'm not going to be sure about my results because I only was able to run 1 or 2 MCMC chains. It never converged. I'm like, now I'm really frustrated and I want to just write my paper, be done with it. And yeah, you get all that. So it should be fast for many reasons. Then ideally, if we can avoid it, we don't want to do any averaging, because averaging throws information away. And, to first order, let's just not do it. I mean, we can always decide later that we only look at a few points, but let's not just start averaging right at the beginning. I mean, it's like, what for? We have all this beautiful data, let's just organize it in a useful way. And this is sort of another one that I find important sometimes, also for that reason that I'm lazy, and like I wouldn't really want to check a lot of things. If I have many nuisance parameters, if I have a binning scheme that I put in, if I made some redshift bins, and then I made some mask with, and then I had a filter, and then I had this filter function. Yeah, every single time I invent some, or I have some other step in my pipeline, I had the smoothing on it, I had this redshift. Each of them I have to always go back and check, right? Like how strongly does my result depend on that thing? So as soon as there's more than 0 such parameters, it becomes a lot of work. And the more such nuisance parameters you have, the worse it gets. And so that's why I'm trying to really get away from having, all these extra parameters. So can we avoid it? And if we can, I think we should. And this is a sort of theoretical thing. There's some idea about symmetries underlying the space that you're covering. And then almost everything I talk about today is purely, I assume, isotropic ideas, isotropic statistics. Not limited to that at all, though. And so you should be thinking about, okay, what's missing? Like, what other metric would you have if you're designing your perfect statistic for whatever you have in mind, whether it might be the dark matter density locally or some other examples we've heard already. Okay, so I'm just going to go through some of the ideas we laid out in this first paper with Arka a couple of years ago now, I guess. And here's the setup. So, right, so all our red dots here, that's our galaxies. And then what we said is do the following. Just follow along on this very short computer program that implements the idea. So what we're going to do is we have all these red input data points. what we're going to do is we're going to throw down random points now. And these are my little blue points here. I'm going to throw randomly in the same volume. So I will uniformly sample that volume by throwing down lots and lots of these points. As soon as we threw one point down, we're going to go, oh, what's my first nearest neighbor? So my first nearest neighbor of the data to this first randomly distributed point. Okay, I record that number, and then I'm going to go to another point, it's a random point, and I say, okay, what's my first nearest neighbor? Okay, I record that distance or the volume. I like the volume, but many of the plots we show in distance. And so we do that for all these points. So we throw down 1 million points, or let's throw down 1 billion. Then it's just super smooth. You know, we measure exactly a smooth, well, we have now 1 billion measurements for all these random points. What's their first nearest data point? A lot of the points, I mean, so all the points in here, you know, if I have another blue point in this yellow circle, it'll also find this one as the nearest neighbor, right? So there's many points that are always going to find the same galaxy as the nearest neighbor. And in fact, if you've learned about tessellations, you know, that's how you could think about your Voronoi tessellation. All the points that have that point as the nearest neighbor, that makes up the Voronoi cell of that. And all the points that have that point as the nearest neighbor, and where the second nearest neighbor is at the same distance, that's at the face of the Voronoi tessellation. So Voronoi tessellations are already built into this, but we're not going to talk about tessellations anymore after this. But anyhow, so we have 1 billion measurements of just distances. So now I have a list of numbers of distances. And so what do? We say, just sort it. Sort the array. So now we've got a sorted list from the smallest to the biggest. And then we just say, okay, which fraction of the points is less than a particular value? Well, for that, what we do is we just say every measurement has the same weight, 1 over the number of measurements that we have, so 1 billionth in our case. So the y-axis goes from 0 to 1 in increments of 1 billionth, because we have 1 billion measurements that will make up this curve. And so what this is an empirical cumulative distribution function, right? It gives you the probability of finding this measurement at this, having this value or less. That's just from sorting. It's a rank statistic. And normally that's great. The thing is with CDFs though, they can be really boring because they always look the same shape. They're very S-like, and you're like, meh, you know. So people love to plot PDFs because they have a, you know, which is just the derivative of that function. They like the derivatives better because, you know, they have more potential to look slightly more interesting than always the same S function. We did not make that choice because for a derivative, that is kind of like choosing a length scale or a binning scale. And we said, no. Anyhow, and so what we do instead is actually a very easy trick where we just plot the CDF now on a log scale, and then they still look boring, but always in the same way where they sort of asymptote 1. But what's nice on the left side is you can see the tail very well. So you can really go down and you sort of see, you know, the first 100 measurements, you can totally see their structure. That's nice. And so, but a good trick to do is what is called a peak CDF is once you reach 0.5 in the probability, you plot 1 minus the CDF and you see the other side of the tail. And so now this is a thing that looks a little bit closer to a PDF. You know, if you think of a Gaussian, you know, it has sort of a peak, but the peak is just at the median. And so here, let me just give you an example, so you get a feeling for what these things look like. So I took this image and then I smoothed it with a spherical top hat of 4 pixels in radius, 8 pixels in radius, 16 pixels, and so on. And then I plot in the back, you see the histograms. You know, so the blue one would be the one for 1. But here in blue is this peak CDF for the same image. And in a way, you know, of course, because it's closely, the back is closely related because it's the derivative of this one. But you see how in both cases, because we're on a logarithmic scale, you can see the tail very nicely in this statistic, right? And also you see what smoothing does. Smoothing brings down the variance. And so in both cases, the width of the curve goes way down. And once you smooth like crazy, which is this gray case, so the 256 zone, you almost wiped out all the information, right? So the variance, is almost zero at that point. But that's also a good way to keep thinking about any cosmology or other things, knowing about how that change, how these functions change as you change the smoothing radius. That's a lot of the things we talk about. What is the variance at a given scale? And here, obviously, it's very non-Gaussian, and you have very strong tails. And some tails, depending on the smoothing radius, might react quicker or less quick of how easily they're destroyed by averaging. Okay, so this was purely pedagogical, so you get a little bit of feel of what are these functions, and don't think of it as a PDF, but you still can get some intuition that you can read similar things off of that. So now let's just do it. We plot a few more of those peaked CDFs. And what I haven't highlighted yet is that we can do this for all the Ks, for my first nearest neighbor, second nearest neighbor, third nearest neighbor, fourth, 100th, 10,000th nearest neighbor. So I can make a huge number of these long lists of numbers. And in fact, we actually store them as linearly interpolated functions. So we can actually compress it back down. So, but now you have 1,000 smooth functions that you can do easy operations on. Right, and because it's an interpolated function, you can ask for the value at any given point. You can do all sorts of things you might want to do easily. And you don't work with binned values. So it's a joy to work with because you work with functions and not with short lists of numbers. And actually, the coolest thing you can do is you can subtract some of these from each other. So if you subtract, so now if you imagine if I have the third nearest neighbor CDF, so from each point I go to the third nearest neighbor. What I know is such a sphere can have 2 points inside of it, right? 2 points or less. Now, if I go to the fourth nearest neighbor, it might have 3 or less in it. So if I subtract from the probability that I have 3 points or less inside of it, the probability that I have 2 or less inside of it, what remains is that I have exactly 3 inside of it. So now I get this really cool, you get this super nice thing where by just subtracting always 2 from each other, 2 neighboring ones, we get these very informative functions, which are the probability of finding exactly 0, 1, 2, or 3 points in a sphere, and now for all possible spheres. And so traditionally, people actually talked about this statistic before. It's called the counts in cells statistic. But the way they measured it is by throwing down random spheres. They threw down 1 million spheres of that size and then counted. Okay, so what fraction did I have 0 points inside? What fraction did I have 1 point inside? But so after throwing a million or a billion spheres, all they got was a single value, or sort of single value of this volume here. And they would have found, like if in this case of having a 10 megaparsec sphere, they would have had less than 1% chance of getting exactly 3 points, about 6% of finding 2, about, I don't know, 30% of finding 1, and almost 80% of finding 0 in there. It adds up to 1, not the way I just said it. But the nice thing here, we did one simple procedure and we got for all possible spheres that you might throw down in the statistics works out very nice. And I'm going way too slow, I'm realizing, okay. So this is just to say that there is a wonderful math that had been worked out really in the 70s, and part of it already in the 50s in statistics textbooks. And but Arka did a great job of summarizing all of this. And here's sort of that particular thing I was highlighting is to get this probability of finding exactly K points for a given volume is really just subtracting 2 of these CDFs that we've measured. And so again, these things are very simple because it's probabilities. it's actually nice to work with probabilities and not PDFs because you don't depend on the DVs. The other thing to point out is there's a very strong connection to all these endpoint functions that you learn about in all cosmology classes in quantum field theory, all the 2 point, 3 point, 4 point, 5 point, all that stuff's actually is already part of any of these distributions, making up these P of Ks. And that whole math is well known of how they connect. Okay, and just quickly, in the Poisson case, there's a very clear functional form of what you're going to find for these CDFs. It's called the Erlang distribution. And people use this to model call centers. Actually, about how calls arrive at a call center has to do with the Poisson case. So, but if you just know a single K, you can predict all others from it. That means it's like you have a Poisson, you apply the Poisson on the Poisson many times, and that just gives you what is the expectation of finding 3 points in a certain sphere, and so on. The beautiful result is for Gaussian random fields, you just need 2 of these distributions, and if you have those 2, you can predict all others. And that's the beauty of the Gaussian field. Again, it only has 2 free things in it, which is the mean density and the variance as a function of scale, which here we write as a volume. And so I put some code online where I told Mathematica to write out all these formulae up to finding 20 points as a function of the sphere radius that you throw down. So you can download that at our GitHub repository. You want to make predictions for a Gaussian random field. So that, check mark on predictability for our statistic. Okay, then here's just some examples of how this might look like in our cosmological setting. So if we took about 10 to the 5 points in a gigaparsec volume and distribute them totally at random, we would expect this peaked CDF in orange here. If we look then at the dark matter particles, where we also take 10 to the 5 randomly out of a Quixote simulation that was in a gigaparsec volume, also the same number of particles, you see the difference that we find more large distances. So that's the voids, that's the underdense region. So in all the points, where you have voids now, like from those points, you have to go further until you finally find your first nearest neighbor. Yes, because it's lower density. And the same thing, oops, wrong button. And at the same time, you see a little bit of a shift also on the left side. But also the median value, you see, is a little bit larger than the median value in the Poisson case. And for halos now, they're even more clustered, so the median moves even further. And you also see you have these much larger distances, much bigger underdensities of voids or underdensities of halos. So they're even more clustered. So you can imagine looking at those functions, you can start getting an intuition of how clustered is it and how they encode it. And here's same thing for those P of Ks, so those numbers of particles per cells of a given size. Okay, let's see. Actually, how much time do I have left? 78 minutes. Okay, I was having so much fun right at the beginning, so let me speed up a little bit on a couple of things. But the first thing that we did is just qualitatively say, okay, let's just compare it to our usual 2-point function analysis. And do we expect in this very classic Fisher statistic analysis, would we see an improvement measuring cosmological parameters for some imagined, very theoretical halo sample, purely halos from an n-body simulation, nothing fancy about biasing or any realistic, survey geometry or anything like that. But nevertheless, comparing apples to apples in the sense that It's the same number of objects. It's the same range of scales we're analyzing as a two-point analysis. And we saw a huge improvement immediately. And so that was like, okay, this is fun. This is exciting. Let's keep going. One of the nifty things to point out is if just looking for the best fit sigma 8 parameter, when we do the analysis with only a single CDF, the first nearest neighbor CDF, or whether we do it with 2, with 3, or with 4 of those distributions, we keep getting better constraints, but we can see in this particular sample, after 4, we're pretty much done. You know, the constraint doesn't get much better because for this particular sample, there is just not that much more information in it. So to much smaller scale you go, or the more crazy clustered it is, the more of those distributions will still have something interesting in them. And that in some sense will be a parameter that you will adjust to your own analysis of given the data you have. But you know, it's sort of a choice you will make later, like in the sense that when you measure, when you do all the measurements, you first don't have to think about any of that. What are the scale cuts I'm looking at? You know, what is the analysis I want to do later? All the measurements you just do without thinking about any sort of nuisance parameters or particular things related to your sample. And then let me just highlight that this works super well also for cross correlations of doing, now asking, is this set of points that I have connected in any way to another set of points? Are they statistically correlated? And in fact, the thing we could show is that we actually do better than correlation, because normally when you have correlation, that just tells you that there is a linear correlation between your random variables. But a much stronger statement is, are they statistically dependent on each other at all? And again, in probabilities, that's actually a very simple statement. If things are totally uncorrelated, then the CDFs just multiply because probabilities multiply. So if I have, you know, 2 distributions where you now think about their joint distribution, if they totally uncorrelated, then the joint distribution will have a CDF that's just multiplying the 2 marginal CDFs. That's it. And so all we're doing is we're comparing, you know, the clever thing was how to actually measure the joint CDF, but then we just subtract out the individual CDFs multiplied. And if there's something remaining, then there is some dependence. And this is really much stronger than just a correlation. Any dependence will show up. And so on Wikipedia, all our source of knowledge, if we, you know, these are examples where you have things where the correlation coefficient is 0, but obviously they're statistically dependent. You know, X and Y are clearly strongly dependent. Otherwise, we wouldn't be making these shapes. And so all of these, this statistic will pick up, and your usual correlation analysis won't. And so that's very handy. Okay, so I said those things in Word, and it's sort of a very strong, clear effect, and it's particularly pronounced actually when you suffer from shot noise, like when you don't have a lot of points. The statistic is also very nice to use because it already builds in the whole Poisson expectation that you have if it were shot noise. And so you can very easily look for deviations from shot noise. Because remember, we can make 1 billion measurements. So our measurement approach, you know, is totally smooth. So even if I have only 3 galaxies, I will extract very smooth function for the first nearest neighbor distribution. So that's a very handy thing that we've used for some applications already. It's also highly predictable because all the work people have done to predict counts in cells in the past can immediately be used to just add up those counts in cells and you get the CDF predictions out directly. Of course, all the other things people do using simulations works great. Arka that I played with, just spherical collapse modeling directly, also worked really well, at least for scales, sort of 15, 20 megaparsecs and above, where a lot of the cosmological analysis is being done. So a lot of the things then go more into how do you think about biasing and the like. And let me just, was just one thing in the repository. I also put in one new little IPython notebook for you to play with on so-called levy flights. And levy flights is sort of a very simple way of making a very clustered distribution. It's just a random walk. So you go to one point, then you pick a random angle, and then you draw a jump of how far you're going to go from a power law. And François Mandelbrot and a lot of the French school have studied these over the last decades. And there's a lot of literature on this in many applications in very wide-ranging set of fields. I mean, from financial things to biology. But it gives you sort of a little example of sort of a worked example. If you have a particular field, you don't know yet of how do I characterize it. And so it gives you all the examples of make useful plots on PDFs, P of Ks, these counts in cells and so on. Yeah, check it out. So the nice thing I think about our statistic is that it's both the estimator and the statistic in the same role. Like very often people tell you about, oh, this is the statistic, and then they talk to you about what's the optimal estimator for that statistic. And in our case, you notice that didn't even show up. It was purely even the procedure telling you how the measurement works also then becomes the whole discussion of your statistic. Okay, so here's a few examples of the things I showed. Bits from the first two papers. We've used it for characterizing results of M-body simulations. We also looked into a particular biasing description of how you go from halos to galaxies. And found also there that the KNN added a lot to the usual 2-point analysis. And so it was also useful in that context. We applied it to an actual observational data set. It was a very simple question we asked. Are the 1,000 best red mapper clusters clustered? It was a very simple question. It turns out they're very clustered. And it was easily detectable. Then we've also done the case where you're cross-correlating a discrete set with a continuous map. So you might do that for the CMB and foreground clusters. You might do this for lensing, when you start with lensing maps and some particular foreground galaxies you're interested in. You have so many applications for that. And then I'm going to show just a couple slides more from some of the recent work I've been doing with Sandy, where essentially we're trying to sort of go through all the key things we need in a full forward model. So the thing we're thinking about is DESI, which will have 100 million galaxies and a very complicated mask and all sorts of bright star masks being masked out. And then they have fiber robots that they can't all get as close as you want them to. And so then you have these fiber collisions. So in some regions where there's a lot of galaxies, not all of them will have redshifts. And so there's some nasty selection effects. And so we were thinking, okay, how do we build a whole forward model? And one of the first approaches here was we did this on very high resolution Abacus Summit simulations, doing it on full light cone. So that then allowed us to actually cut out really a full sky thing. It has enough halos in the simulations to actually have a place where galaxies could potentially live. So then you need to think about, okay, what's my description of how galaxies live in halos? And we showed some of that work in here. And then in this latest one, which is not on archive yet, we sort of blow it up and do go also to another dimension. So let me just show that. Because of course, when we observe galaxies, particularly spectroscopic survey, along the line of sight component is not a spatial component, right? It's just a velocity thing. And so it has multiple effects. So in clusters, you get this fingers of God effect, and intermediate scales, you get this tightening. Filaments are thinner than they should be. As they sort of falling in, you have this Kaiser bias, I guess people think about it, or redshift space distortions, essentially. And so we can sort of use that fact and turn that into a net positive, by just saying, okay, instead of averaging, and just doing one single radius, let's do the one along the line of sight, and let's do the radius, on the sky. And then we just keep a 2D distribution. Same thing, you know, it's a CDF. Okay, so now I have a CDF, but in both directions. So we just sorted everything of how many distances do we have in the lower left corner of these 2D things. And everything else just totally generalizes. In fact, the measurement is exactly the same. It's just what we store is different. But it made a huge impact, actually, in improving, you know, how we can recover, in this case, just parameters of the HOD. Just show briefly, going from this 1D KNN that I described for most of the talk, just to the 2D version, splitting it up in these two parameters, go from the green contours to the red contours. So independent of what parameters we're constraining here, like every time you gain. And it's not surprising because, you know, subhalos, inhalos have a particular velocity thing. And so if you're now putting galaxies in there, you get just a much better constraint if you didn't average out because you keep the correlations between on the sky and along the line of sight. And then one more thing, then we also did the DDKNN. So that's now, instead of going to random points in the universe, we just go to only the galaxies. And at the galaxies, we ask, what's my first nearest galaxy? That's not me. And do exactly the same procedure. Like it's exactly the same code. It's really just one character changes in the analysis pipeline. And this one is then the same thing, but density weighted. And having a density weighted version, particular for how you model galaxies, helps you a lot because all your galaxies, you're populating the dense parts of the universe. So now you upweight the things that are in dense regions. And that also helped, whoops, very much. Anyhow, so let me just conclude. Essentially, I think all the things I said at the beginning about interpretable and fast, I didn't say, but it's n log n, and it really runs very fast. It's faster than your 2-point function in essentially all cases. And it's, you know, once you spend some time with it, it's interpretable, quite easy to use, and it's definitely robust. So I think, and we didn't do a lot of averaging, or any, and we didn't invent any new nuisance parameters. So that's why we're liking it and are sort of eager to apply it to a lot of things because it's actually fun to use. It's not, and you know, anyhow, I hope you enjoy it and you get a chance to use it and give a try of the GitHub repository that I put there so that you make it easy for you to play with it. All right, thanks so much.
Thanks, Tom, for such a nice talk on such a complex topic. So let's start with the question answer session. So,
hi, I'm not sure if I missed it when you were talking, but from the first couple of slides that you said, it just seems like you, I'm not sure how you model the interactions. Like if you just if you do the CDF thing, it just seems like there's no reason for it to clump or cluster, or, you know, it should just eventually be like a probability entropy thing. So it should just spread out. So I was not sure how you model that.
Right. It's wonderful. You're already thinking about it in a physical way of like, you know, how would I model now the evolution of that thing? It would be wonderful to code it in this language, but we didn't do anything sophisticated like that here. All we're thinking about is using it as a description of what is. There's no evolution, there's no, it's like, yes, when we have the simulation data, like, yeah, we have all the evolution, but at each step, we just apply the procedure to just show how does this function change, right? So, but there is, you know, so the whole purpose of it is really as a descriptive tool, and that goes under the word of summary statistic. How does this statistic summarize the state, you know, of the data?
Okay, so you don't actually predict the form of large-scale structure or structuring or nonlinear structure or whatever.
Yeah, so I went over that a bit fast. So there is many ways of predicting the large-scale structure. So whether it be the simulations or more analytical frameworks. And in some analytic frameworks, yes, there we can write down the evolution for these CDFs directly.
Right.
And then there's a few people, other folks already did this for counts in cells. So these are other GitHubs where you could download their approach of predicting very closely related statistics, so you can easily derive it from their codes to do ours.
Right, because at the
But
end, I think
these
you
are
just-
approximations. Yeah.
At the end, you just mentioned that you can sort of give more weight to those nodes which have like more dense or something like that. So that could be one way to sort of clump them together. Is that something related to what happened?
Right. In your theoretical model, which you will work on the next year, you should predict both the density weighted statistic and also the not density weighted statistic. And if you match both, then you know you made a good theoretical model.
Got it, thanks.
So, so there is online question.
Yeah, hi. Am I audible?
I can hear you.
Yeah, okay. So I have two questions. First is, the way I have understood it is, as long as you can define distance between your points, you can do KNN statistics. It doesn't matter if it's a galaxy survey or if it's, for example, catalog of quasars or whatever, right? I can take any data that I have, and as long as I have a metric, therefore a definition of a distance, I should be able to do KNN statistic on it.
Absolutely. And essentially everything will follow through all the results I talked about. And so you could take very abstract spaces, and
Exactly.
And it would be still very useful. And I think the applications you should look for are the ones where your expectation is a uniform prior. Like, so where you're looking for the difference from a Poisson sample uniform, that's going to be the easiest case to immediately apply our results. For other situations, you could adopt it to it, but I think that would be the case. Where it will go through the easiest.
Right. Okay. Just second small question is, you in the very second slide of your presentation, you said summary statistics, but you don't want to use averages.
Right.
That almost seems paradoxical to me, in the sense, if you're doing summary statistics, at some point you will be averaging over something, right? I mean, I understand it did not come up in KNN statistics, but why is that one of the design goals that you put for your summary statistics itself?
There is one averaging that I did that I sort of hid under the rug, right? Which was including the distance.
Exactly.
I did the x squared plus y squared. But then at the very end, I told you I actually don't have to. I could have kept the three separate and just think of it as as a 3D CDF. And then I really would have not averaged. But yeah, it's sort of philosophical. I mean, there's also a way to think about it. In CDFs. You could also think about it, okay, if you read out a particular value, that's like having a very large bin. From that place
exactly
to down to zero.
Exactly.
Yeah, I don't want to go so much,
Okay.
I don't want to oversell this either, but all I'm saying is we just order and we never touch the values and directly average. So yeah, it's a bit more subtle, but but I don't know any other good words to describe that.
Yeah. Okay.
Yeah. So it's not clear to me, how does the CDF depend on the number of dimensions in which you put your points? So for example, if you have points distributed in 3 dimensions, okay, and you do this procedure and make your CDF. And then what you do is you project all your points on a plane and then carry out the procedure. So will the CDFs look very different or will they look similar?
Okay, so for a Poisson, that's exactly the one where it doesn't matter. So there it'll always look the same. I mean, so if you started with a 10-dimensional Poisson and you project it down, all you notice is, it's a different density. I mean, because it's a 2-dimensional density now, not a 10-dimensional. But it's exactly the one that has no memory function. There's no way for you to find out how that thing was made. In which the statistics here is so nice that actually it tells you exactly that only a single one of those nearest neighbor distributions is enough to get all others. So even if you measured the 10th nearest neighbor distribution, we could get the 9th and the 8th, but also the 11th and the 12th, because knowledge of one is enough for this.
Okay, thank you.
Hi, Tom.
we can actually cut it out. So you can talk during the tea break. So thank you, Tom, for a nice talk again. So we can move on to the next speaker.